I lost ya. It's gone. We are doing a process today called linear programming. And linear programming is one of the things that, well, it's used tons in business because the process we've been going through is exactly what they do. They have to figure out, okay, how much do we want to spend on labor? How much can we afford to spend on electricity? How much can we afford to spend on this? And then how much do we make? You know, that for business, that's always key. So what they want to do is they want to keep their costs down as low as possible while still being able to get the profit that they want. And that means there's a lot of things to keep track of at one time. And that whole process is called linear programming, where they figure out, okay, where should we produce? How much should we put out for our business every day here? How many products should we put out there so that we can make the most money possible? And that's really business strategy. So what we want to do is to solve problems using linear programming. Now, a big portion of this, in fact, almost all of it is stuff we've already done. But we have to learn, well, what do you do with it all when you put it all together? So 3.3 was really the start of this. We have to know how to graph these in order to see here's where they should produce. So this first question we're going to come back to in a little while. It says you want to spend no more than $40 for at most 15 tomato plants. So you've been around the neighborhood. You've seen that the people that are in your neighborhood don't really have gardens. And tomatoes can be really expensive at the store. So you're thinking, I'm going to start up my own business here. I'm going to grow tomatoes. They'll be right here, and in the neighborhood I can sell these. But you only have space for those 15 tomato plants, and you only have $40. So you want to maximize the pounds of tomato you get, because that's how people pay for tomatoes. You put the tomato on a little scale, and they tell you how much it is. How many of each plant should you buy? And justify your answer. So like I said, we'll come back to this one. We're going to do some non-word problem ones first. And then we'll come back and put this one together and do it from start to finish. So on the next page, oops, where's the one that's not a word problem? Okay. This one. So this one says, what point is in the feasible region maximizes P for the objective function P equals 2x plus y? Well, it's missing an important step, and that important step is, you know where we were doing our double shading yesterday, and now we're going to see some triple shading? That region where we have double or triple shading is called the feasible region. It's called the feasible region because that's where businesses want to produce. They want to be in the feasible region, and it's because the highest profit is always found at one of the vertices of that feasible region. So we need that feasible region to say, hey, here's where you should produce. And in fact, you should produce right here because that's where you're going to make the most money. So what is this all about? We haven't seen that before. That's called an objective function. And P usually stands for profit. So once we do our graphing and we figure out where that feasible region is, then we'll come back and use this. We'll try to figure out where's the biggest profit for our company. So, constraints. Well, that's a fancy name for the stuff we've been graphing. Those are all inequalities. They're things that hold the business back. Obviously, you can't just make as many products as possible and expect to make money. If you flood the market with a product, then the price goes down. So they have to keep this, well, reasonable, which is why they have constraints. So we have x plus 2y is less than or equal to 5. And the first thing I would do with that is find my zeros. That's a nice standard form equation. It shouldn't be too hard to find the zeros. 0 in the x would give me 5 halves, or 2.5 for y. Now with these, it's going to be okay if we use decimals because we're talking about real world stuff. And then if we put a 0 in for y, x is going to need to be 5 to make that say 5 equals 5. So that's my first boundary line that I have to graph. 0, 2.5, and 5, 0. And we will want to color code these so we can make sure we've got everything right. So maybe grab some colored pencils now too and circle that. That way we can definitely see, hey, here's where that double, or in some cases triple, shading is So that boundary line, 0, 2.5, and 5, 0. And it has an equals bar, so that'll be solid. And if I test 0, 0 really quick, this will say 0 is less than or equal to 5. Is 0 less than or equal to 5? Sure it is. So we're going to shade towards 0, 0. So we had those colored pencils out. So 0, 2.5, 5, 0, solid line, shaded down. Probably hard to see in the back too, so let me scoot that up. Anybody need more time on that? Well, let's go get our second boundary line. That one is x minus y, so I'm changing colors. Is less than or equal to 2. Well, there's another nice standard form equation. But I'm going to have to be careful with the negatives. If x is 0, this is gone. Negative of something is 2. What would that be? Negative 2. I mean, that's the only way. If negative of something is 2, it has to be the negative of negative 2. If the y is 0, this is going to be 2. So 0, negative 2, 2, 0. That one does have an equals bar, so it'll be solid. Then we have to figure out which way to shade. So in x minus y is less than or equal to 2. If I test 0, 0, it's going to say 0 is less than or equal to 2. Is that true? So let's shade towards 0, 0 for the blue line. In this case, that means up. Now I look at the last two constraints. And I'm going to switch colors. Okay, all that's doing is telling me to stay in quadrant 1. It's saying I have to stay where x is positive and y is positive, which makes sense with businesses because if you're talking about a product, x and y, it's always going to be positive. So what I need to do is just basically cut this off right here and not look at any of the other quadrants, just quadrant 1. 2, 3, and 4 are out. And figure out, well, where's my double shading in quadrant 1? And that is everything in here. And when I say in here, the name of that in here is the feasible region. So that met all 4 of the constraints that they had, and it gave us that. Now, here's even better news. If they want to know where they're supposed to produce to make the most profit, the answer is always at one of the vertices of this figure. Remember, vertices are where you have 2 sides that come together in a point. So there's only 4 places for us to check. Either up here at 0, 2.5, we know that because we graphed it. Down here at 0, 0. Over here at 2, 0. Or up here at what looks like 3, 1. Now, since I said up here at what looks like 3, 1, I would want to check that point in my inequalities and make sure that it works for both. So I'm going back up here and I'm going to put 3 and 1 in for x and y, and I want to make sure that I get what's on the other side. 3 plus 2 is 5. Good. But it can't just work. for 1. It has to work for all of them. 3 minus 1 is 2. It works. And it's definitely bigger than 0. We didn't have any negative numbers in there. So now, the business we're talking about should produce at one of those 4 spots. Well, how do we know which one? Because there's something we haven't used yet. Right here. Objective function. An objective means, what are you trying to do? They're trying to maximize their profits. So we're going to take those 4 black ordered pairs that we have right there, and we are going to put them in for X and Y and see which one of them gives us the most money. And sometimes they don't just ask which one maximizes, sometimes they also say which one minimizes. The one that gives us the smaller one will minimize. So 0, 2.5. Put a 0 in here, put 2.5 in here, you get 2.5. Put 0 and 0 in there, you get nowhere, you get nothing, 0. Put 2 and 0 in there, 2 times 2 is 4, 4 plus 0 is 4. So far that's our biggest amount. Put in a 3 and a 1, 2 times 3 is 6, 6 plus 1 is 7. So this objective function is maximized at 7, the ordered pair 3, 1. And it's minimized at 0, producing 0 and 0. But this was multiple choice, so we better go back and see what they wanted. What point in the feasible region maximizes? So which one gave us the biggest numbers? C. 3, 1. All that to answer a multiple choice question, right? Each of these problems takes a while. They just do. Each of these problems has you graphing and then trying to figure out where is that feasible region and how do I go from there. That's why today we're going to 2. That's all we're going to get to. Okay? That was one of them. The other one, the tomato problem. So let's go back and talk tomatoes. And we're going to need graph paper, and I know there's not one in there, so I'm going to get you some graph paper. And we're going to do all of it. We're going to set up the constraints. We are going to figure out how to graph it, and then we are going to tell these people how many of each plant they should buy so they can maximize the number of pounds. Sticking to each other. So it's human. Now, when you're graphing these and you're going to solve them by graphing, you really need to have a straight edge. Not necessarily a ruler, but like your calculator lid usually makes a good straight edge. You can use the calculator lid to draw a straight line. Thank you. Or the edge of your notebook. That makes a good one. So you have binders, folders, that kind of stuff. Because when we're solving by graphing, if we mess up on the graphing, we're supposed to all the way through. And the other thing we do, the reason I gave you graphing calculators is because we can check with the graphing calculator. This is where I think that those two intersect, but I better use my graphing calculator to see. So here's what I'm going to have to do. I'm going to have to clear all of this out here. So that I have enough space to put a graph in. All right, first things first. What a business truly cares about is making money. So how do they make money with these tomatoes? They maximize the number of pounds that it's going to produce. So I'm going to have my objective function be P equals, so that it stands for pounds. And now I just need to look up there and try to find something about pounds in this information. Do you see anything about pounds along these plants? See it, Tori? Where are you looking? You have those signs over there, right? What do you know? This one's 8 pounds per plant, and this one's 10 pounds per plant. So I'll have my Romas be X, and I'll have my cherries be Y, and that will be 8X plus 10Y. Now that's the first thing I write. It's the last thing I do any math with. Because remember, I have to figure out how do I get all the rest of this information graphed to get a feasible region. So the next thing we do, they're called constraints. Things that hold you back. Constraints. What was one of the constraints up there? You could only spend 40 bucks. So if we have one about money, we know it has to be less than or equal to 40 bucks. Ryan, pay attention up here. Quit trying to listen to music. Okay. Alrighty. What do you know about money from any of the information that's up there so far? Yeah, you got to go to the sign again, right? So 2x plus 3y has to be less than or equal to 40 bucks. What else is holding it back? They only have room for 15 tomato plants. Yeah, that's it. That's it. So something has to be less than or equal to 15. Did they say you're going to buy twice as many Roma as cherry or anything like that anywhere in here? So we just know you're going to buy both. Now, I warned you about this in yesterday's and when I was doing the homework. If you walk into the nursery and say, I'd like to buy a -3 cherry tomato plants, they will laugh you out of there. So we need to say X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. Because it's real rare. In fact, it'd be silly to go in and say, I'd like to buy 0 cherry tomato plants. That doesn't make any sense. So we know it has to be greater than or equal to 0. Now, we want this graphed. In order for us to graph it, we need to know what to use for intervals. And that means it'd be a good idea to go after the zeros for one of these, just to give us an idea of what type of numbers we should put on this. So remember, we're saying, pretend this is equals. If x is 0, cover that up, it's going to be 40/3. 40/3. So I think, okay, how many times does 3 go into 4? Well, it goes into the 4 once with a remainder of 10. So then it'll go into that 10 3 times with the remainder of 1. When I graph it, I probably just want to think it as 13 and a third. Then, this is easier. If I don't buy any of that type of tomato, it's $2 a piece and I have $40. How many can I buy? That one's nice. So that'll be our first graph. Now, why did I do that one and not the second one? Because this one had bigger numbers, and we're trying to figure out what kind of numbers we should put on our graph. So we have to be able to go to at least 20, which is good news, because my grid here is 20 by 20. So you will probably want to make sure that you can draw a 20 by 20 on that paper. Why did I only do first quadrant? It has to be positive, exactly. We said x has to be greater than or equal to 0 and y has to be greater than or equal to 0. Now here's where we kind of have to be really careful about our graphing, and that's because, again, if we don't get it graphically, we will get it with the graphing calculator, and I'm actually going to show you how to do that. But if we could do these perfect, it would be really great. It would make our job a lot easier at figuring out where they intersect. So that red one I had up there was 0, 13 1/3, and 20, 0. Actually kind of cheating and grabbing my straight line drawer up here. Here's another nice thing about word problems. Remember, this was about money. So we have to think, would it make sense to say they've got an unlimited amount of money and they can just get as many as they want out here? That makes no sense. The shading has to be done. It has to be. It's money. You don't have an endless supply of money. Then we can switch colors and go back to the other one, which was you've only got room for so many plants. If you don't buy any of the cherry tomatoes, how many of the other ones do you have to get? Yeah, you get 15 plants. Vice versa, it's just going to be 0, 15, and 15, 0. If you don't get any of the one, you need the 15 plants from the other. So change in colors and go to 15, 0, and 0, 15. Try to use some kind of straight edge. Did you have space for a limited amount of plants? So we know the shading is under that last line. And that means this will be our feasible region. We already have it in quadrant 1, so we know that's where it has to be. So the next step is, well, what points should we put into the objective function? What are the vertices here? The good news is, well, we graphed this one. We know this one is that goofy 13 1/3 thing. So 0, 40/3. This is pretty obviously 0, 0. This one, we just got done graphing. That's 15, 0. But now comes the tough one. Right there. Now, if I had to guess, I would say it belonged here and here, wherever that is. But I don't want to guess, because chances are pretty good if that's the tough one to find, that's the one I need. You know, that's the one I have to find. So here's what I do to get it. I go back to these top two inequalities. And I treat them as if they're lines. So I had this one in red. I pretend they're lines. And I solve it for y, and I put it in my calculator. So I would subtract 2x from both sides and divide by 3. Now we know we were absolutely right about that 40/3 because that's where we're supposed to be graphing if we graph this. Go up 40/3 and then down 2/3. And I want to see where does it hit my other line that I had to graph, which was x plus y equals 15. That one's nice and easy to get y by itself. You just subtract the x. Jazz, head up, pay attention. This takes a lot of work. So what we're going to do is we're going to put this into our calculator and this into our calculator, and we're going to find where they intersect. I don't know, on yours, was it like a perfect spot? You could actually see it is perfectly right here. See, that generally doesn't happen when we have these long lines. So let's get these into the GC. And let's see, what was that first one? Parentheses, negative 2/3, x, and that was plus 40/3. All right, so there's my first line, and the second was negative x plus 15. That was easy to solve the y. But we have to think about what window we should use. Remember, we said we shouldn't use negatives. So let's go into window. 0. Well, x and y were the maximum number of plants. What did we say was the maximum number of plants they had room? 15. So let's just make 20 the top number, and then we'll definitely see what we need to see. So 0 to 20 for both of these should work. And we get graph. And now all we're going to have to do is call up Blinky, so Blinky can tell us where those fit. Do you remember how to call it Blinky? Second trace. Number 5. And enter 3 times. And Blinky says, give me something hard. That was obviously the point 5, 10. So that's our last vertex. Now, how else could we have done that? Algebraically. We could use substitution or elimination, but it's kind of nice to just have Blinky to do all that for us. So, you know, if you're thinking, boy, if I would have had these red and blue equations, I would have just multiplied this one by -2 and done it by elimination, and that goes faster for you. Yeah, do it that way. Do it by hand. But we can also make use of Blinky, and that makes sure we also got to see where those lines were. In case we messed up graphing those lines, we've now got them. Whew! One more step. We're almost there. What did we find all those for? Now put into the objective function. So let's go back and grab the objective function. The objective function was about the pounds of tomatoes. So that was P equals 8x plus 10y. Now we're going to put these numbers in there and we're going to see what we get. Ugh, 40 thirds. Okay, well, if we put that in here, that'll give us 400 thirds. So we better see what that is as a decimal as we look at the pounds. Thirds equals 133 1/3 pounds. Sounds like a lot of pounds. That might be our max there, but we'll see. We'll see what else happens. If you put 0 in for x and 0 in for y, what are you going to get? Yeah, this is them saying, I give up. All my plants died. I'm done. 15 and 0. We need 8 times 15. Hey, that's 120. That's even more than that. We've got one more to go. And that's the 5 and the 10. So 5 times 8 will give us 40. 10 times 10 is 100. 40 plus 100. Last thing we would do is we just write one sentence to put this all together so that when the boss comes in, we can tell him this is exactly what you want to do. The maximum pounds of 140 uses, and now we have to remember which one was x and which one was y. Well, one was X. What type of tomato was the top one? Roma. So 5 Roma plants and 10 cherry tomato plants. Woo! You see how the math was nothing new? All math we've done before. Okay. Are we in that place? We are, aren't we? So since each one of these probably takes, well, it was about 20 minutes with us talking through it and going through it. Each one might take you 5 to 10 minutes. I only have about 30 of them for you today. Just in case. That's a joke. That's a joke, and not 30. That would not be fair. And some of these you don't have to do all the way through. So that's it. 10, 11, 12, 17, and 18.